Hi, this is Group 6 with Matthew, Javi, George, and Ian. This is for Aero446. We're doing a Parker probe analysis.
So an introduction to the Parker probe is that it is a current active NASA mission in collaboration with the Johns Hopkins APL, launched in 2018. The goal was to touch the sun or study the sun's corona. The subsystems it has are solar arrays for power, high gain antenna, low gain antennas, and fan beam antennas for communications slash tracking telemetry and control, carbon composite shield for thermal protection, hydrogen thrusters for propulsion, and reaction wheels for EDCS. Next slide. An analysis on the power systems are that the probe has two retractable solar arrays, a primary section when that is used when it is distant from the sun, and a secondary section used as the sun is approached. The incident angle is adjusted depending on where it is. It also has a solar array cooling system. It is actively cooled with pressurized water, the first of its kind. The minimum power requirement for the mission was 482 watts, and it was designed to meet this at 0.25 AU. The design considerations taken into account were variable solar incident intensity, extreme temperatures, and rapid solar degradation. It stores power in batteries and has an internally redundant power distributions unit. Next slide.
Communication system utilizes the NASA Deep Space Network for RF communications. It uses a high gain antenna, mainly for communications of 0.6 meter diameter. It uses the Ka band because of the high throughput to return as much data as possible. Mainly for downlinking science data at a rate of 167 kilobits per second at 1 AU. And then for TT&C, there are a set of fan beam antennas that use the X band because of the efficient guaranteed delivery of commands, and it saves uplink bandwidth. And then also includes a set of low beam antennas for backup and redundant antennas that support uplink and telemetry as well. The thermal systems use a passive carbon composite cone-shaped thermal protection system with two outer carbon layers, inner carbon foam, and they have white coating on the outside for thermal protection with sun-facing side. Other passive instrumentation for thermal control are radiators, louvers, and MLI. Active thermal control includes a solar cooling array system. Heaters are also on board to maintain temperature when the spacecraft is away from the sun.
For the ADCS system, the Parker probe used reaction wheels to face towards the sun. Unfortunately, through my research, I couldn't find the exact sizing or dimensions of the wheels, nor how much, but we can assume that there was at least an extra one for redundancy. What an ADCS program could have looked like is sensors determining the current position and torque disturbances, and then having the desired orientation, most likely facing towards the sun, and therefore command torque. Then you would have a control law and reaction wheel full state feedback to change the attitude of your spacecraft. What else would this have been used for? You would be able to alter the Parker probe to be ready for delta V burns, to face in, to be able to change orbits. This probe was in a 7-time Venus flyby course and would need a lot of adjustments for to prepare any delta V burns.
So some highlights from the mission. After launching in 2018, the probe conducted 7 flybys of Venus, which you can see marked as green dots on the timeline. Those were to reduce speed and drop the perihelion distance, and with reduced perihelion distance, you can see the orange maximum speed increasing. In December 2024, the probe conducted its closest flyby of the sun within 6.1 million kilometers, reaching speeds of 191 kilometers per second, making it the fastest human-made object ever flown. During flight around the sun, thermal management and ADCS systems were critical in protecting sensitive instruments and managing heat shield alignment. Communication with ground stations was cut off during the scientific phase of the orbit, which was within a quarter of an AU of the sun, and as such, communication windows were an important part of mission planning. Some scientific advancements. The Parker Solar Probe measured magnetic switchbacks and Alfvén waves, confirming that both of these occurrences contribute to coronal heating. It observed magnetic rogue waves and a cosmic dust-free zone around the sun. The probe measured plasma using the field sensor, which is an array of magnetometers, and the sweep sensor, which is a sensor that can measure proton, electron, and helium ion velocity, density, and temperature. And you can see some footage from flying through those coronal streamers below. Next slide.
So to conclude, the Parker probe launched in 2018 to explore the sun's corona, and to do this, it required several complex engineering systems with various redundancies in case of failure. These systems we talked about were the retractable liquid-cooled solar arrays, the antenna configurations for communications, the carbon-carbon composite for thermal protection, reaction wheels for stability, and all of these engineering systems culminated in several groundbreaking scientific observations and achievements. This made the mission a success, and it is slated to end conducting its last perihelion on June 19th, 2025. Next are sources. Thank you so much for watching.